Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on January 19th, 2026, just 3 days ago. It introduces a framework called Think3D that transforms standard vision models from passive 2D observers into active 3D thinkers, improving spatial reasoning accuracy by about 8% on key benchmarks without requiring any new training. The paper is titled Think3D, Thinking with Space for Spatial Reasoning. And as we'll see shortly, the results suggest that tool-augmented exploration might be the missing link for genuine spatial intelligence in AI agents. And for those interested in the implementation, the authors have shared their code on GitHub. So Figure 1 illustrates the core concept. On the left, we see the prior Think with Images approach, where the model answers questions by detecting 2D regions and zooming in on pixels. But on the right, the new Think with Space framework operates differently. Here, the agent actively requests specific 3D viewpoints, like a top-down or egocentric angle, and manipulates a reconstructed point cloud. This allows it to understand true spatial relationships, rather than just analyzing a flat image. Well, Figure 1 just sketched the general setup. Now, in Figure 2, we walk through the method details step by step. On the left, in Panel A, the diagram maps out the interaction loop. The vision language model takes a question and video input, but instead of guessing immediately, it sends commands to the 3D manipulation toolkit. This toolkit generates a new rendered image which feeds back into the model's memory, allowing it to iteratively observe, manipulate, and reflect before giving a final answer. Then on the right, Panel B illustrates the mechanics inside that toolkit, where the system reconstructs a point cloud and applies the requested camera transformations to synthesize the exact view the agent needs. So, having seen the method in Figure 2, Table 1 now quantifies the impact on spatial reasoning benchmarks. Focusing on the middle rows, we see that for advanced models like GPT 4.1, simply plugging in the Think3D framework boosts average accuracy by over 11%, all without additional training. In contrast, the bottom section shows that smaller models, such as QN3, initially struggle to use the tools effectively. But crucially, the final row demonstrates that with reinforcement learning, the smaller model learns the necessary exploration strategies, unlocking a solid 7% gain. Alright, moving from static images to dynamic video, Table 2 presents results on the VSI Bench tiny dataset. The middle rows show that large proprietary models, like GPT 4.1 and Gemini 2.5 Pro, consistently gain performance, boosting their averages by roughly 3 to 6%. However, the bottom section reveals a different story for the smaller QN3 model. Initially, simply adding the tool actually hurts its performance on tasks like route planning. But as the final row demonstrates, once the model is trained with reinforcement learning to use the tool properly, that same metric leaps up by nearly 13%. So, while the tables showed the performance gains, Figure 3 now visualizes the actual reasoning process in action. In the top example, the user asks what lies behind their current position. Instead of guessing, the agent first requests a top-down view to grasp the global layout, and then synthesizes a specific egocentric view looking backward to confirm the door's location. Crucially, the bottom panel compares the untuned model against the reinforcement learning version. We see that while the base model struggles with camera direction, the trained model systematically uses the coordinate axes and the reconstructed view to correctly deduce the movement. Well, Figure 3 showed the qualitative behavior, and now Table 3 identifies which components actually matter. The first row sets the baseline. Surprisingly, the second row shows that just adding raw 3D reconstruction without guidance actually lowers accuracy, likely because the model gets lost in the geometry. But in the third row, adding a camera anchor fixes this, causing a major performance jump. Finally, the bottom rows confirm that enabling active camera selection and egocentric views unlocks the highest accuracy, reaching over 66% on blank. Wrapping up, Think3D shows that genuine spatial intelligence comes from active exploration, not just passive viewing. By giving models the tools to manipulate 3D space, we see immediate gains for large models, and a clear path for smaller ones via reinforcement learning. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.